여기
이거. 이거. All right.
Silent presentation.
Exactly.
It's a new style. No words.
Just interpret.
Words are cheap.
Okay. Yeah, so just want to share what I was working on for a while. And the kind of motivation here, so it's about spectral induced polarization. What that means is basically you got a multiple frequency channels or time channels. So sometimes, like it's a simple model, they explain that using COCO or whatever other IP models. So here's an example. Then here's an app generated before. So this is the conductivity, or I think resistivity is a little bit more intuitive in kind of DC survey. So if you look at the curve, so that's a real part. So it started from large value and then decreased. So I think that's the zero frequency when you're fully charged up, and then you're getting discharged as you go higher frequency. Because you got no time. Like if that's really fast frequency, then there's no time to build up the charge. So that's what's happening. And also not only that, you got a imaginary part, which is like, it's like a phase delay. It takes time, right? Like to build up the charge takes the time, meaning you're gonna have some sort of phase information. And then that's actually in the imaginary part. And that's in frequency, but what we're measuring is in time. So if I transfer that into time domain, so here I'm convolving with the Stepoff kernel, and then outputting it. So if you don't convolve it, like if you just transform it, that's an impulse response. But like that's not what we're measuring. What we're measuring is pretty close to a Stepoff, right? Like we're putting some sort of like a pulse looks like this, right? And then here we're assuming we got infinitely long on time, and then turn that off, right? So that's a step off, and that's the response looks like. The resistivity is similar to voltage if you think about the Ohm's law. So that's very similar to what you're measuring, right? So you could measure from like 1 millisecond to 10 seconds, for instance. And then what you're doing is like you do some like a stackings and processing. But at the end of the day, what you're using is like that time window from, what's that, 800 to 1400 milliseconds, right? So you integrate this time window, get one value. For instance, here is like 40 milliseconds. That's your data, which is an apparent chargeability. And that's done. So your processing is done. Now you take this 1 point datum. Well, you got multiple source and receiver position, meaning you got tons of data, although you got a single time channel, and then you recover chargeability model. Well, you first do the DC, then chargeability. That's what usually do. But the interesting thing here, okay, that's what we're doing, but we're ignoring all this other data set, right? Which can be pretty useful. Right? So there's a chance, let's say, okay, let's say we are interested in material have tau 0.1, or let's say we got tau 10. So that actually changes pretty big difference in your responses. So 1. So I was explaining just that, like a kind of bit of motivation with the spectral IP. And so not only tau, you can change C, right? Frequency component, 0.3, 0.4, 0.5, 6, 7, 9. So actually that changes a lot. Like it depends upon your polarization character. So now, like rather than discarding all of those time channel that anyway you're measuring, let's take that account, invert that, rather than recovering just the chargeability value, recover all 3 parameters, and then see if that's the additional information. That's anywhere where we're measuring it. It's there rather than just discarding it. Let's take that account, invert it, recover, see if how much additional information we can get. So that's a big motivation that I have here.
So can you remind me historically why the 800 to 1400 is significant? Why did they do that window originally?
I don't have I think it's almost like a machine learning, I guess. That's in what's called Newman standard. I think they did a lot of IP survey. So for instance, I think what that could be, let's say they are interested in certain tau. Okay, they're interested in a certain mineralization, have a certain tau or a certain C. Then there could be some sweet spot of the time window that they could see that, right? But they're not interested in other things, right? For instance, then I think that's what it happened. I guess that's my guess. Otherwise, there's no point. It's like, oh, that time window could see something they want to see, but other window is not quite interested.
That makes sense.
Yeah. But I think so here, like, okay, that was the first order, and that actually worked well. Okay, but there's other time channel. Why don't we actually take that account and invert it? So that's my motivation.
Yeah, so I think part of that's right on, because they were, looking for mineralization, sulfides. All of this, the fundamental research all came out of Newmont. That's where the powerhouse was. So they were the driving force. And then other people would come along and they do time, but they do different channels, and then realize we can't calibrate anything. Like, you're doing something, I'm doing something. Let's make a standard. So then they just decided on this as the Newmont standard, and at least that gave then everybody an opportunity to collect data and then compare it. You collect time domain data, I collect time domain data. We can at least see if we're in the right ballpark. So I think that was the real motivation.
Right. Yeah. So that was the motivation on my end, because I asked like a whole bunch of other people who's like actually acquiring DC and IP data. I think that's their usual process. And then their processing is really kind of focused on to go that a certain time window and get the one single IP data. So that's how they build up all of their processing software and then interpretation. So yeah, I think that makes sense. Then like at the end of the day, they're kind of discarding it. But I think here, I don't know, like I want to show some potential, because it seems like people are pretty pessimistic about, okay, like getting 10 time channel, adding 10 more time channel doesn't really add information. So that was my impression when I was talking to like a Sid Visser or other guys who's acquiring the IP data. So I'm still not sure is that right or not? But, so that's the paper. And we're using a linear solution. So I think that the focus here is like I want to develop. Okay, that's one part. For a mineral application, I want to develop a spectral IP inversion code that can extract that, right? And then part of the reason I think they didn't have a right tool, I guess, to extract that information. So I think that's potentially a reason. So I want to develop an efficient code that can actually take the large-scale 3D DC and IP data to cover those multiple parameters. So that's the main I think goal here. And using the linear kernel has a lot of advantages because it's actually much cheaper. If you take that as a nonlinear problem, or for instance, like how Arhus guys are doing, for instance, they're computing all of the things in frequency, convolving their waveform, and then coming back to time domain. I think that's fine in 1D or 2D, but like once you're moving into 3D, that doesn't really work, I guess. I don't know, if you got a really big computer, no problem. Parallelize it, but I think there's no reason why we could just directly in time domain, and we can actually use that just a linear kernel, which is actually already developed a long time ago. Okay. And the question here, what is the pseudo chargeability here? This guy, how do we derive it? Because like here's an option, you can use COCO, or so that if you choose COCO, the problem is okay. It's defined in frequency domain. So anyway, you need to compute in frequency and somehow convert in time. That's the same problem. Like if you want to do that each single voxel, let's say you got 1 million cells and you need to do that transform 1 million times. So you can parallelize it, but I think it's still pretty expensive and computational point of view. So, okay, can we use some explicitly? Is there any other function that I can use it explicitly? Then I'm good to go. Right? So I think the first time that I heard was actually from Eldad, and he was pretty excited. Oh, I found like a new function and a new ODE that he can solve. But I think it was 1870, something like that. I think a German researcher actually found this function and used it for a number of other applications. So in polymer study, I think that's the main function. So there, I think they use other functions like CoCol or whatever others, or dielectric relaxation. So I think it's not like it's not known. It's known for a while. It has been used for other applications, but interestingly, in our application for IP, CoCol was the main one, has been used for a while. So people don't really know if I start talking about stretch exponential, but I think we can still use it. And by using explicit time function, you can actually do that convert. You don't need to do that conversion, right? So you just need to somehow plug this into here, right? Then you're good to go. Right? J is like it's a DC sensitivity, so you've already got that. Then you can actually compute the IP. So here's a little bit of like a math. So that was the step function. Remember that stretch exponential. Then it's a step off. So use a step function. Then if you want to write the step off function, you need to start from 1, subtract your step function. So that's a step function u. But the required output is like, so this is u, so 1 minus u is step off. So it's simple. But it's interesting because like people use different terminology. Oh, it's a step function then. Oh, is that a step on or step off? So it's kind of blurred. And then like once like this, people start with their terminology, they have no idea what they're talking about. So I think it's pretty important to make it really clear what that is.
So in your case, U step is the step on.
Yes, yes. I defined it, so. Right, yeah. It's still blurred. What is that? Is that step on or step off? It's not Python standard. I need to put on, I guess.
Oh, is that right?
Oh, like a Pythonic is actually like, rather than like using just a part of the word, I think just use full. I think.
That's fine.
It's too long then, so I'm doing a trade-off. So that's a step off function, right? Like convolving it to step off function. That's the result, right? Then by taking the derivative, you can get the impulse function. So that's a result if you have a CoCo model, for instance, if you directly transform that into time, that what you get is the impulse function. And that's the explicit form of stretch exponential in time domain. So that's how it looks like. Then for when like that's the pseudo chargeability. That's an impulse. You need to convolve it with a waveform like this. So you need to convolve with that, right? So that's the real waveform. And actually, in real waveform, that's not just a single period. You got multiple periods. So let's say, I think I asked John. John is doing like 80 stacks, for instance, or 40 stacks.
John's on the
About 80,
Hi,
yeah.
John.
Hey.
Yeah, is that right?
Yeah, it's about 80 stacks we do generally.
Okay. Yeah, so it depends, right? And then there's a practical stuff you need to be careful with. Oh, you cannot really use the step off, for instance, right? You just need to take account what is your waveform. then like, okay, in practice you're doing 80 stacks. Do we need to do 80 times of this computation? Or like, okay, you could just do 2 or 1, or you could just assume a step off, for instance. So that's kind of practical questions. Anyway, so that's sort of the background. And then once you solve those problems, then you're set in terms of force simulation. So for instance, you can, let's say, generate this model. So that's a porphyry model. And there are multiple units. I think it probably makes sense, I guess. I asked Thibaut what is a reasonable porphyry model. And I think he said yes, so probably okay. I think he's the only really geologic person that I know. So the main structure here is a halo, like this orange guy, and the mineralization and clay. There's some porphyry, which is purple one, and stone. Okay. And there are 3 chargeable units, which is halo, mineralization, and the clay. So by just using the typical like DCNIP inversion, what you can recover is like all 3 of them, right? But you cannot really distinguish what's what. So if you can distinguish all 3 of them somehow, that'll be great. And so I actually designed it that I could do it. Well, it's a synthetic example. So what the main difference between the halo and the mineralization is time constant. So time constants depend upon the size of the grain. So let's say you got a very fine grain or fine mineralization, you're going to get really small time constant. But if you get like coarse grain size or like coarse mineralization, which is probably what people want to find, I guess, and then you're going to get large time constants. And the clay and halo has a different frequency component. So C also determines how it decays. It's more like a distribution in frequency domain. So if you go back here, so if I change C from 0.2, it's very smooth, right? Like in terms of distribution in frequency domain. But if I change that to 0.7, that's very sharp, right? And in time, it's actually like decaying a little bit. I'm not sure, it's not a decay rate, but I think it actually still makes it fast decaying. Right?
You can tell it's dropping off faster.
Right. So anyway, so C can make some difference in your data as well. And usually clay has a large C compared to the other. So I assigned large C for clay and then smaller C for halo and the mineralization. So that's the setup. So in theory, if I can recover all those 3 parameters, I can distinguish clay, halo, and the mineralization. So I think that was the main the story.
In terms of the hardware, do you know if clays are harder to measure, to close to like the noise level, late time channel?
That is quite true. So because if you think about the C data, resistive one has large signal, right? If you got resistive conductivity, then you're going to get large signal, for instance. So clay is very conductive, meaning your actual voltage will be pretty small. So I think, in terms of noise level, clay has less chance to be seen. So if you got like a chargeable clay, then IP response in terms of voltage probably pretty small.
I was thinking more in terms of IP, your IP signal, if the shape of your curve in time is more influenced in the late time, is it harder to pick out in your data?
I'm not sure that I'm getting, what's the
I was
question?
looking at your initial curve, right? Like
Yeah.
Because you're measuring in time, you're not measuring frequency.
Yes.
And most of your signal is actually happening near the late times.
Right, that really depends upon tau, right?
For the clay, it's usually the reverse. Like the clay has a very fast decay, so it's hard to pick up because it's in a very, very early time, and sometimes it's as decayed even before you start measuring. It's in the end now.
Yeah, so there are like some challenges, and then also the measured time band it's pretty small because it's designed to see that integrate time channel, right? But I think there are some movements, okay, well, if there's no problem, you just need to increase the higher sampling rate, right? So there are some people doing it, but I think that's not quite standard in mining industry. So I think we probably need to show the value. Then I think that some people might take that up. Okay, we probably need to increase higher, like a sampling rate. I think that's sort of the goal, but I'm not sure where that's going. Anyway. So that's the setup, and then that's the conductivity. Okay, so we got resistive stuff, conductive halo, conductive clay, right, and also conductive mineralization zone. Not very conductive, but like modestly conductive. That's a chargeability, so you can see any difference. So I just designed. Okay, I got exactly the same chargeability for all three. And tau is different, right? Mineralization has much greater tau. So I'm assuming my mineralization zone has a much greater coarse, like a mineralized grain size. And C is different between clay and the halo, and also mineralization. So the black is the large value, C value. And if you look at the data, that looks like that. So that's a DC data. So here, remember, I got the 5 lines of the data. It's not that big, survey, but it's 5 lines of data. So each line is separate, so it's not like each line, it's not connected. Right? So I'm just doing a dipole inline, which is kind of typical, I guess. Right. So that's DC data, and IP data at Ollie time. So that's 1 millisecond. That's pretty Ollie, I think. The data that I've got was like a 0.05, like a 0.0. John, what was your Ollie's time channel?
Previous time channel, I think, is about 30 milliseconds.
Right. So I think 1 millisecond is pretty Ollie in terms of like a mining standard. But anyway, so it's a synthetic example where. And then IP data at 4 seconds. That looks like that.
Yeah, you can really see.
Yeah. So that's quite different, right? Like, so that's a good sign. Well, your data is different. So there's some things that we can actually extract. That is true. Yeah. So here I'm designing in that way we could actually extract something. Yeah. But if you see what our guys doing, I think they're doing less stacks. So it's always trade-off, right? Like if you're doing the 80 stacks, then it takes a while, right? But if you're just doing the 4 stacks or 2 stacks, but measuring longer time channels, then I think doing a 4 stack, I think it's not a big deal, for instance. So I think it depends. Like, so that's a question. Okay, it depends upon what you really want to do or what you want to see. You can actually change your sort of like a measurement system, and then that's always a trade-off. So
getting what you're saying, yeah. But what's the cost benefit of longer?
Well, like it's always time, right? Like how much time it takes, right? To record the data, right?
But what's the advantage of doing only 4 steps?
Oh, yeah. So I think here the goal is getting a really high quality, less noisy, like a single time integrate data, right? But if you're actually taking account like a multiple time channels and fitting that, I think that little bit of noise in that a certain time channel is kind of fine, I think. And then you can do other processing. So yeah.
Does that make sense, Tom? So it's just a trade-off between like either you can stack a whole bunch, so that's what you're using your time for, or you stack less but measure for longer times. So it's like a time versus signal to noise trade-off.
Yeah. Oh. So yeah, we stack that long so that we can stack out the noise as best we can. The more stacks you have, the better you can really beat down that signal to noise.
How long a base period do you use? Because Seogi's looking here at 4 seconds.
Yeah, we generally do a 2-second off time. That's pretty typical.
Yeah, twice longer. I think that's okay.
Oh.
So that's what our guys using, 4 seconds. They're using 16-second period.
Yeah.
And also,
you could wait very long.
and also the other trick that you could do, rather than using a half-duty cycle, you can do a full-duty cycle.
Okay, what is sorry, man?
A half-duty cycle is a step off, like turning the current off.
Yeah.
Right. So you don't really need to do it. Like if you got a way to extract the step off from the full-duty cycle, so you can actually use a full-duty cycle, then you can still use just 8 seconds and get the 4-second data. So, anyway. So there are a number of details here. But, and so now I'm moving to an inversion. So that's the 4 problem. So we got the data. Data looks like, okay, there's some interesting things going on to extract. And let's move on to inversion, which is an interesting part.
Just a quick question. Are you using the octave mesh for this or the tensor mesh?
Tensor mesh. I think we got all the pieces, but it's not quite there yet. So we'll push that later. But,
yeah, fair enough.
I haven't got it. And also, I was thinking about that, but I think it's not the point of this paper.
Yeah, no, totally. It's just like, that's just an implementation question.
Right. I think here's some, okay. So here's a IP inversion methodology. And this is your predicted data. Okay. That's still a linear kernel, but now in terms of like a eta tau c, it's not quite a linear kernel. It's a nonlinear kernel. So it's different linear. And now your IP data is a function of conductivity, chargeability, tau c. So here SC stands for stretch exponential. So I just want to distinguish this from COCO. And pseudo chargeability, this guy is a function of chargeability, tau, and c. And then conductivity is known, right? We do a DC inversion. We cover that. Assume that it's pretty close to the true conductivity, and you can just generate the sensitivity function here. Okay, so that's the setup. And now the data looks like that. So we got a multiple time channel, meaning you got a pseudo chargeability at each time channel. Let's say you got a 20 time channel, then you're going to get pseudo chargeability at 20. But that's not what we want to recover, right? But if you go back and think about what the conventional workflow is recovering, it's just one of the pseudo chargeability, okay, at certain time channel. And now my model, here is the M eta, M tau, MC, right? So I got 3 parameters that I want to recover. Okay. And well, like the usual question is, okay, what is my model, right? Well, that's kind of the first question that we need to ask, but sometimes that's kind of underestimated because like there's usually a typical choice. But here it's a little bit new problem. Okay, how do you choose model? It's a part of the research question. And I'm not going to go there, but I think here's an option. Okay, you can choose either log or linear tau. Okay, so what's your choice? How do you choose it? So that was a part of my research question. And then, okay, how do we map my model to actual physical property value? So here's the details. Like you guys probably know that like we got these wire maps, right? Which is actually pretty cool. Then by using it, you can be pretty flexible, which is actually really cool. So here it's very easy to do. Now let's say I know pretty well about the tau. Okay, in this region I'm expecting tau 0.5. Okay, so I don't want to invert that. So you can easily fix the tau and just invert for chargeability and C. Or a whole bunch of other combinations possible by using wire map, which is actually kind of cool. I didn't mention it here, but it's a bit of details, but I think in practice, that's a kind of cool things to do. Although, yeah, sometimes people don't really care, but I think that's an important point.
Do we actually have a detailed tutorial on that? Wires?
No, that would be a good thing to put together because it is like conceptually it's actually not too involved, but it is definitely something to get your head wrapped around. Sure.
Yeah, like if you screw up the sort of the syntax of the process in one step, it's a really great tool that you can't use, I guess.
It won't just won't work. So here you're turning it off for the rag. You're just not putting a wire for the rag, and then for the emissive function. How are you using a wire to?
Oh, this is just for regularization.
Just for the rag.
Yeah. So, well, I think I was actually explaining a bit, right? Like, this is basically just an injection matrix.
Yeah,
right?
that's effectively all the wire map does. It basically says like have a giant model, and like these 6 parameters are tau, these are data, C, and then like it maps them to where they need to go.
So I didn't just slip in, but I think I tried to explain it what actually it does. So for tau, for instance, if tau was a second variable, that looks like that. But it doesn't necessarily has to be, right? Tau can be wherever you want. So that if you just set the first variable, then the model just changes. Anyway, so the choice is either log or exponential, log or linear. So I ended up choosing all the log variable, so I could show, okay. Yeah, it's like usual stuff, data misfit, uncertainty, and here's your combo objective function. So I think I just kind of want to mention what were the pieces that I had to use and how useful it was. So this is the combo objective function, right? Like we got the regularization function, which have smoothness and smallness, but each parameter has that, right? So you need to have each of them. Each parameter needs some regularization. So I think I'm just kind of looping over. So I is eta, tau, c, and we're actually summing that over to have a single regularization. Yeah. Yeah. So I think there are a lot of details, and then if there weren't those functionality, it would have been really hard to actually implement in practice because that actually could be a lot of work. And then at the end, we're actually putting some constraint for each 3 variables, and we're minimizing this function using projected Gaussian. Yeah.
But you missed a function, you're only adding, let's say you don't want to include tau, you'll only be adding the
exactly. So that's a good point. So I think I probably need some sort of like a constant here, I guess.
I'm not thinking the 5b, right? Because
no, I think it's just the regularization function, right?
But you need to not, like if you don't want to invert for tau, you need to not include it, right? Because otherwise you miss the function.
So in that case, I pass the tau directly to problem. The tau is a known value. So I can pass tau.
And then, sorry, though, I think, correct me if I'm wrong, but I think Dom's question is just then you wouldn't regularize on tau. So you would drop that component in the combo regularization.
Yeah. Yeah.
Now I'm wondering, because right now, like technically, if your model is three model parameter long,
right?
Your misfit function would have a gradient on the tau if you have your misfit function.
Yeah. So I think I'm doing it smart in the code. So if tau is not, so for instance, like if the mapping for tau is not set, then I'm not like actually computing it. So that's a beauty of the wire maps. I think then you just need to that case actually outputs the 0. So and then I make sure I'm not computing the sensitivity for tau. So it's just like a 0. So
same problem.
Yeah. So yeah, I think that there's details, I guess. If you want to do that types of like a flexible way to I just want to set the tau and I'm just invert it for 2 variables. So that case, things can be kind of complicated without that like a framework or structure, which is actually important. And I think there's a value because let's say now you want to do even more complicated things. I kind of want to start from I just don't know I know the tau, but I'm pretty sure, but I think I'm still not exactly sure. So I invert that first, invert the other data first without the tau. Then, okay, I'm pretty close. Now I want to turn on tau and invert all of them together, for instance. Then I think there's and that's possible with this structure, which could be interesting, I think. So there could be other research that, okay, what are the good strategies to invert? I think, so that's probably an interesting thing, but I'm not going there.
And just like on an implementation side, there's 2 ways to achieve what Seogi's talking about with dropping the regularization term. So you could, when you're setting it up, just not include it. Or if you wanted to do in the second example, sort of the ability to turn it on and off. If you set the multiplier on that then to 0, then it just won't evaluate.
Yeah, and directly
yeah.
Yeah, so yes, I think that that inversion part, I didn't work that much, so it's already done. So what I had to do, I just like weave together, and so what I did actually, I wrote the sensitivity function, and then weave them together like that we can invert. Actually, that part was pretty fast because it was a cool part. So inversion methodology part is done. I'm going to show you guys some of this example. Well, the focus of the paper is 3D, but I think we've anyway developed 2D, so I'm going to start from 2D, which is kind of nice. And then I'm going to build up, okay, what are my models, and what are the setup that I need to use? Because like the bottleneck of this problem, you got 3 variables, which could be really non-unique. So how do you tackle that? That could be a part of issue. So rather than starting from 3D, which could be more challenging, I'm going to start from simple, easier problem like 2D, and then build up the setup, and then just apply that in 3D. So that's sort of my strategy. And the other thing is, there are too many conventional workflow, but so Yuval and did the other work. So they worked on spectral IP inversion problem a long time ago. I'm not sure, 15 to 20 years ago. So what they did was so I'm going to go back to just. Right. So what they did, actually, like you could just invert each time channel separately, right? So rather than inverting all of them together, you just got the DC inversion, generate the sensitivity function, and invert each pseudo chargeability separately. And once you got 3D volume of like having multiple time channels, you can kind of set up a small inverse problem for each voxel, then recover a chargeability time constancy. So that's what they have done. Right, so I think that's exactly what I've done in Airborne. It's the same workflow. And so I kind of need to compare, okay, what are the values, right? Inverting all of them together compared to just like do a separate inversion and extracting some intrinsic parameters. So that's something that I also want to show here. What are the values? So I'm kind of starting from the first problem, and it's actually the same problem if you think about that in terms of inverse problem, because okay, your data will probably have some, maybe not. So your IP data is equal to, let's say that's a time I is a time channel, and J delta. So what you're recovering is this guy, right? So you're going to get eta at the first time channel, but in 3D or 2D. Okay. And then what you're doing, so I'm going to pick up a single pixel. Let's say I got a J pixel here. And then in terms of time, okay. So yeah, in this direction. Then you're going to get a time curve, right? But you got this guys at each voxel in 3D or 2D, okay? So you can set up an inverse problem basically using the same regularization function and recover all 3 parameters. So now, let's say you got a 2D grid. And then your data, observed data, is same as eta tilde or estimated. Right. So you do a separate inversion, you recover that. Now that's your observed data, and then you want to predict the data, fit this data, and recover all 3 parameters. Right. So there's a lot of similarity. Like what's changing is that we're changing the observed data and the forward kernel, but basically it's the same problem. So here I think we can learn a lot just solving it. And the main problem was, okay, what is my model? So here's a comparison. I don't know, if you actually know well about the IP, I think intuitive choice is eta, log, tau, and c. So tau is varying like kind of logarithmically, but eta is like linear. I think there are probably some argue, but I think if you think about how we're inverting it, that's like probably linear. And C is linear as well. So C changes from 0 to 1. Okay. So I think that could be an intuitive choice. Or you could just take the log, all of them together. And then, or you could choose other things. So what I did is, okay, so I can compute the gradient and see if how the gradient, how like a distribution of the gradients looks like. Sorry. So that was the each inversion result at the early time channel, late time channel. They are decaying, right, in terms of amplitude. So like I did for each time channels. Now I'm extracting. So here's an interesting plot. And then if I chose this one, actually inversion is like falling into local minima. So it doesn't really converge to my target misfit. So I was curious, okay, why is that? What's the problem? And by plotting the gradient, it's actually getting clear. So if you look at the histogram of the gradient, then chargeability has much larger value compared to the others, right? So you need some sort of balancing here. And then you could actually like put some constant, or you can choose your model. So that's your choice. So my choice is, okay, how about like taking the log for all the variables? Then actually like a histogram is getting more compact. And actually that inversion converges pretty well. So that makes it quite robust. And I was actually reading the RO's paper, and that's what they're doing. So it's a bit opposite way, but they didn't mention anything. But I think that's probably why they're choosing it, or not. I'm not sure. But,
Did you try that, just keeping the C in the linear domain and then just doing log and tau and eta?
No, I haven't tried. So I could definitely try. No problem. Yeah, I think it's a certain case. So I think that's for this example. So I'm not 100% sure that's really totally extendable for a whole bunch of other cases. So I think there's a cases maybe that actually choosing linear might be better. So I'm not sure. I think log seems like a robust option, I guess. So as a default, I think I would choose log. And I think that's probably like it's kind of subtle, right? So
And then when you chose log, did you go back and kind of think about what your regularization parameters or what your regularization functionals are? Because now, I mean, if you're working with the log, your function is really different, right?
yeah.
So did you go back and alter that on the basis of what you thought you're going to try to get out physically, but you're still working with the log of something?
Not quite like the way that I like had to tackle it's kind of like a trial and error. So this part I got some intuition, but when I'm actually working in the inversion to make it robust, like setting up the parameters, I think I was like purely trial and errors. I wasn't 100% sure, like okay, what exactly I had to change. But I think I didn't have to change that much. So I was basically used mostly default option. There was some. No, I think actually I used like almost default option for regularization. Same kind of like impact on alpha S and alpha X was that or something. And for 3D problem, that was 2D like I got a field example, but like let's say your lines are pretty far, then I just had to use the alpha Y large, which is kind of like typical. So I didn't use that like really fancier parameters here.
And so when you did the switch, you then regularized. Did you regularize on the log of those parameters, or did you?
Oh, I regularized on the log of the parameters.
Okay.
So I'm regularizing on the model.
Okay. Because that's also like something that you could try if you were interested, is actually like do the mapping and regularize on linear parameters.
Yeah.
I don't know, because I mean that actually could be interesting of like what are you doing if you're changing just your data misfit versus the regularization.
I think there's definitely a.
There's lots of, yeah.
So I think that's a kind of trade-off. Okay.
Yeah, absolutely. Absolutely.
What's the question? And I think yes, I think that really depends upon like your focus, I guess. So I think now if the question is, okay, what is my model? If that's a specific question we're asking, we definitely need to do it. But I think that was a sort of part. I think it's not main impact, I guess. So I didn't really go through that much details. But I think that's a good point. Okay, and then here's the recovered chargeability, tau, NC. So here, what you could potentially see is like, okay, maybe C. But not quite. I think you can get tau values, but couldn't quite distinguish mineralization, I guess, from this approach. So in terms of resolution, I think conventional approach, you may lose some, right? Because like you're kind of splitting up apart that as a two steps, right? And then that really depends upon how quality pseudo chargeability that you've got from the previous inversion. Each time channels, right? So there's a subtlety, right, in practice. So you need to do a really good job kind of doing, recovering a pseudo chargeability at like each of the time channels. Right? And that the result is really depends upon that part. So that's a bit of like a disadvantage, or could be an advantage, but I think there's a bit of subtlety.
How do you, you need to guarantee you fitting all your time channels equally, right? If you're underfitting, you're late or early.
Right. Yeah. So those are the subtlety in the. Yeah, in theory, it's a robust approach, right? In terms of non-uniqueness, it's actually you're inverting for each time channel, so it's less non-unique compared to the other problems. But there's also kind of a little bit of disadvantage that you need to make sure the quality of those all pseudo chargeability model at 30 time channels for 20 time channels. That could be a disadvantage. Now that's the.
Wait, when you say it's less non-unique, I guess the way I would interpret it as opposite. You've actually put, by inverting them all at once, you've put more constraints. Like you actually have less free parameters, that in between step, right? Because if you invert every single time channel, you actually have like more free parameters than what you end up interpreting at the end. Right? Because you have you have a pseudo chargeability at every single time step.
Okay.
That is way more parameters than having 3 at each voxel.
Well, yeah, but I think at each inversion, like I'm just thinking about each inversion, right? So at a single time, so I think that like a non-uniqueness is actually basically the same as the IP inversion, right? Or this inversion.
Yeah.
So that was sort of my point.
Okay.
And then once you get, like, even though you got 20 time channels more, you got 3 parameters. I think that like increase of 3, I think it's not linear increase. I think that non-uniqueness actually increases exponentially, I guess. Like if you just one parameter, 1 3D variables and 2, I think that's not quite like a linear increase of like not 3 times non-uniques, I guess. Yeah, I'm not.
But when you're inverting though for 3, you're using all the time channels, right? You're not inverting for 3 at a single time channel.
Right.
So if you look at sort of through all time.
Yeah, well, I think that could be a point. Yeah, so in that mindset, we were thinking we're just thinking about a single time channel. Like in terms of non-uniqueness, I think we were like, let's say I got a single time, and we're inverting it, and that's a 3D variable at a single time. It's a fair point. I'm not 100% sure how to defend that. Which one is more non-unique? Yeah, I'll think about that. I'm not 100% sure.
Would be some sort of the ratio between the height of your matrix versus the 3 times number of.
I think if you're getting into that level, I think it's kind of tough, right? Like now, then you need to think about what is the unique data and what are the unique information.
Let's imagine that we're like square, and you want to end up with a square matrix, I guess, if you it's like this or just like this. But then if you do non-uniqueness, that increase the uniqueness of your problem.
That do you have an idea?
Infinity is pretty big. I don't think it much matters. I mean, the deficit to working with time channel is that now you've got all the issues and the regularization, and now you're getting an eta tilde at each. Okay, so that's a non-unique thing, right? And then now you do lots of time channels. So in principle, lots of time channels is actually going to give you an overdetermined system, right? So overdetermined is nice from the point of inversion. So sure, we get, that part of it mathematically is, although still non-unique, it's at least an overdetermined system for 3 parameters. So the degree of non-uniqueness is arguably not so much as if you're in the function space. But then you've got the wrong data, and because of all your parameterizations and whatever you had for everything. So that's you're kind of hooped there. That's something, right? If you just go the other way, then now you still got this huge non-uniqueness that's associated with that. So I have no idea of okay, whether one is more non-unique than I mean, that's there's challenges on both sides.
Anyway, so those are the challenges. So here's if I just do a spectral IP inversion, so that's a chargeability, and that's tau and C. So you can actually see the large tau at the mineralization zone. So so if you're doing really right, you can get higher resolution, and you can distinguish probably like clay having higher C compared to the halo. So I think that's sort of what we're saying as a value. So here, if you're getting the right pieces, then there's some chance to get greater resolution in your inversion. And then now you got the setup, then do a 3D inversion. So this is a 3D inversion result of DC, chargeability, time constants, and C. So I think you can get. Sure. So I think things worked in 2D. So let's move on and apply this. Use the same parameter and apply the 3D inversion. That actually worked well. And so here's the kind of interesting plot. So if you plot the recovered C and the tau in cross plot, you can definitely see the clustering, right? And you could do some sort of classification. Well, this is like an easy case. We know all the parameters. But let's say I pick the large C with the small time constant. That's a clay. And the small C and the intermediate time constant, halo. And if I pick the large tau, that's a mineralization. So, well, there are probably a whole bunch of different ways that you could do a clustering, but here we're just picking a simple threshold. And those are the parameters of the inversion. This is a field example at Saudi Arabia. It's the same porphyry deposit. So this is the DC inversion, and that's a chargeability. That's time constant. And that's so we could do the same practice of plotting in the cross plot. And by looking at here, so these are the time constant, frequency dependency, and I colored by chargeability. So you can definitely see the trend between here and there. So high chargeability, high time constant, small chargeability, small time constant, for instance. That's all like let's say if I do a binary, then you could kind of multiply it like this. Then your rock model, have kind of 3 units, background. Yellow could be a mineralized zone, or a coarse grain zone in your mineralization. And orange could be some sort of mineralization zone, have a smaller grain size, for instance. Could be. I have no idea, actually. There's no drilling here. I have no idea how whether that's really reasonable or not, but just kind of showing the capability of the code. And actually, there are some other details. Okay, mentioned there's repetitive waveforms, and sometimes that's very important to take that account if you really care about the values, like a quantitative value. So I actually implemented it's a linear sum. It's a linear. You could think about it as a superposition of all the step response, because it has a plus, minus, and then you have a time delays. So if you kind of track all of those things, and you can come up with some sort of function, a step function, looks like this, then you need to put that into your pseudocharge when you're computing the pseudochargeability, also computing the sensitivity. Then that's your set. That's a bit of details, but important. Yeah, sensitivity. Yeah, so I think that's it. And it's a kind of research, but what I thought kind of important here. Okay, so we could. I'm not sure. Let's say this is a high quality research. So we could actually do it now with the current framework. But what I was thinking is, let's say there are some pieces, right? Very important pieces like wires and combo objective function. But there's a challenge by itself. It's kind of like like us. We definitely know what's the value, right? Because we're using it, and then we know how helpful it is for our researchers. But in the outside, it's very hard to know that contribution. So I'm still not sure. Definitely how we're selling that, we need to do a high quality research and show how much you can do with that. Right? I think that's the way to really sell, how that framework is important. I think there's no question, but I think that somehow still we need to attribute that part. I'm still not sure how we could do it. So I think that's probably we need to think about. Okay, there are some groundworks, and there are some base functions, base works, which is really important. But it's kind of hard to sell that in the current society, I guess. So yeah, I don't have a really good answer about that, but I think I kind of want to. That was sort of the question that I had when I was working. So I really appreciate it. I finished the research, and then I look back what I have done and what kind of pieces that I needed. So there are some important pieces, and then somehow I want to contribute that. But I think, I don't know, citing SimPEG paper or something, it could be, but I think it seems like not enough, I guess. So there's probably something that we need to think about.
But within the development of the inversion inside paper, I mean, there could be sections on, numerical implementation, and then just, have a section just talking about how things are implemented and how things are connected. I mean, that's quite possible, especially for something like a GeoSci publication.
Yeah, so I actually put that in and I cited. So we could put a bit more details.
I mean, there's a question if you want to go into that, I think, and just scope of the paper, and that's really up to you. Down the road, I think if we have a few papers out that are using some of these things, then actually writing a synthesis or sort of review type paper that talks about actually the underlying structure that enabled that, that's potentially a trajectory forward. Yeah, because it's hard to write a paper just about the combo objective function, but if there's examples like this that we can point to and say this is what it is enabled,
right.
Then that becomes a lot more possible, I think, to get something out there about those things.
Yeah. But still, with the viewpoint of trying to elevate the visibility of what has gone on in the past, I mean, one can insert various things, small sections here or there, appendix here or there, that can really consolidate that, and then it's at least there in a concrete form, and then now you have a global paper.
Yeah.
Okay. But, I agree, trying to elevate some of what you consider to be subtleties, but are actually really important parts, are we should try to do that here. I mean, and the same is true with what you were doing in your stuff. So, yeah, I think that's just a good thing to keep in mind, and then just kind of have that little emphasis sort of slipped in here and there.
Yeah, absolutely. Well, and to that point too, like I think being specific in like acknowledgements as well, like saying, these pieces enabled this work. Like that's also not a bad place to, because then people are sort of less concerned if like they actually understand all of it. Because if it's in the paper, then you want to go into enough detail that people understand it. So like that combination, I think, is potentially a way, at least to elevate it a bit.
Like, you mean that, let's say, a wire maps, for instance, that's like stating, okay, we use the function called wire maps, or is that how you wrote it, or like a?
I guess the wire.
It's not a bad idea.
It's not a bad idea.
You do it for, I use this package from Scikit.
Yeah.
You do it
Yeah.
for other packages, more than ours.
Yeah, no, I think that's actually totally like, so in the like discussion about the implementation, like having a statement that says, in the implementation, we use the SimPEG wire maps to keep track of where all the variables are.
Yeah, so
Like that is totally a fair statement.
Right, that's a good. So we could have a small section that implementation details, and then actually mention what has been used.
Well, and it doesn't even necessarily have to be a small section. Like even in your current implementation, when you talk about the P matrix, for example.
Yeah, or this
Like-
sum has been done using the wire map. This sum has been done using the wire map.
Yeah.
If they want to know how it does, then go to our reference to the website.
Okay. Yeah. Yeah, and finally, I'm going to follow with Lindsay's workflow for SimPEG research. So I'm going to put all the results, notebooks and results and online. I think 2D could be deployed on Binder, so people can actually run it. 3D is a bit better. So.
What I've done with all of my simulations or inversions that are too big to run is I just do like a download at the beginning.
right.
So I just say like rerun is false. And so by default, it'll just download and display the results.
Yeah, so I'll do the same thing. Yeah, and I think I think that's actually nice. That it's a good container that the people can actually reproduce. So yeah, I think that's it.
That's really cool. So
That's nice, Saeed.
Yeah, that's awesome.
Lindsay, that's nice.
John, what do you have for an example over a porphyry?
I don't think I have one. I was looking for one the other week there for Seogi, but yeah, I didn't quite find anything right now. Nothing that I have access to.
Although so we actually started so John and I started working on a small data set that I think it's a fieldwork data set, right?
Yeah, it was the field school for the University of Saskatchewan there over a buried target.
Right. So, well, it's not like in terms of target-wise, not very exciting, but I think it's a metal plate or something like that. Is that right? Metal plate.
Yeah, it's just a steel plate there. Yeah.
But I think in terms of like doing a processing and understanding point of view, it's actually exciting because it's what John is interested. Like it's similar to that inversion, but you can apply that for the data now. So we can consider that the pseudo chargeability as a parent chargeability. And now you want to extract some IP parameters, for instance. So that's what John is interested. So I think I got all the functionality. So so John actually prepared some small data set and then like all procedures of how he's stacking it and then converting that into a window data set. So here I think there's some interesting things we could try. Okay, we could take before the window data, we can just take that raw, like not raw data, but kind of stacked data, then just fit that, recover our local parameters. Or we could just take the window data and fit that and recover local parameters, for instance. And there are a whole bunch of different things that you can think about. Okay, now if you are turning that into a processing problem, because when data is 2D, it's kind of simple. But I think they consider that 2D data, then that distribution of apparent chargeability, or tau and c, is supposed to be pretty smooth. If you're picking, if you're carefully picking the similar size of the dipole and then plotting into a pseudo section, you're not going to get really like a creepy data set. Or like that part could be just noises. So you can actually set up a kind of like fitting problem. And actually you could do some like, I don't know, processing noise reductions and stuff. But I think we're not going to go there. But I think getting the field data set and then showing an example how you can extract that. And then actually we could take the data and invert with the same workflow.
Yeah.
So that'll be a good example.
We actually might be just finishing up a pretty interesting porphyry survey here. So depending on those results, maybe we can look at that one too.
Cool.
Well, thanks, Seogi. A couple other quick updates. We're a little over time, so I'll be fast. I posted an issue. I think you've already taken care of this on a different branch, Devin, but the VRM tests are failing on master right now. And I think you took care of it on the pull request that's with all of DOM stuff. But I was wondering if you could just isolate those specific changes and just do a quick pull request and we can get that working again. Because it's really hard to bring in any form of changes when master's failing. So we can chat about that more afterwards, but it's functioning on the branch that your like the tree mesh acceleration stuff is on.
Which we're going to be working on. So yeah, let's bring that on that part.
Because right now, all that those stuff, the mesh stuff and the VRM stuff are exactly in the same place.
Yeah, but it's not on the master, right?
Yeah.
And so there's VRM stuff that's failing on master, and so if you can just isolate the fix that you've already done, and make a small pull request, not a giant pull request, then we can get it in like today. Because otherwise it sort of stalls any other pull request coming in because it's failing.
Yeah, I think it has something to do with octree meshes.
Yeah.
So whatever fix I did with octree meshes for that to fix my tests, I'll just do it. Yeah.
Yeah.
But then won't it have conflicts?
It will, but it should be like a 2-line conflict because I think this fix is like super simple. I think it's just how you're refining things.
Yeah.
So hopefully it's like 3 lines max, and that's a very easy thing to conflict resolve. So, and then other than that, Dieter pushed some cool plotting code. So that'll be fun to look at, and feel free to provide input on his pull request there.
What sort of things would you do?
It's so that you can scroll through 3D models, so you can plot different slices of your 3D model, and rather than like hooking up a widget to it, I think he's just linked it to the mouse, so you can just scroll and slice through it. So that's pretty slick.
But it's in discretize?
It's in discretize. He just started a pull request. And then there's a couple other small things. I'm just gonna. One of the things, so I started a small pull request, and I'll circulate the link. Just with some of the plotting stuff, it's nice to have a little more control on like plot mesh, for example. Like to get a publication quality figure, like I wanted to go in and change the line width, line color, all of these kinds of things, and we just didn't give you hooks. And so I think like this is a silly little patch, but I think that we should give some thought to how we actually want to expose that to users. I think we could do something like having sort of line style keywords, and because right now I've just thrown them all in like kwargs, which is not great because then if you don't know what the kwarg is and I haven't documented it, then you have no idea. And so down the road, actually, what I think would be kind of cool is to turn the current like plotting actually into an object, and then so that actually all of the styling are just properties that you could swap out. So
Okay.
we set reasonable defaults like what we've done, but then actually you could just swap them out.
Impossible, because under the hood, we're all just calling matplotlib functions, right?
Yeah.
Can we just be able to get all the hookups for all the sub-plotting functions? You know what I mean? So if we have like a dictionary for the in show,
Yeah.
be able to just use any of the keyword arguments.
Yeah. Yeah, I agree. And it's just a question of how to expose that.
Yeah.
Because right now, like if you look at the plot grid, for example, it's like slightly non-trivial because we've got, like, I don't want to pass all the same plotting arguments to how we plot edges, faces, nodes, and the grid lines, right? Because we want different markers for each of those things. And so if I just pass like blanket color everything red, then that doesn't do what you're expecting. Yeah, so like I think going sort of the object route where then just like edge color, edge marker, each of those is a property, and then you can just tweak them and like edge size and whatever. Might be the way to go. And then we just serialize that and pass it all to matplotlib. So give that some thought, and feel free to add comments on that pull request. Cool. Anything else from anyone else? No? That's okay. Perfect. Okay, well, we will reconvene next week.
See you
Oh,
guys.
your paper, by the way, with Craig.
Oh, Craig.
Oh, that's awesome.
Yeah. That.
Teamwork.
Okay, see you guys later.
See ya. Thanks.